Thank you. Hey, my name is Fu. I do some type of form of nondescript cyber. I really miss real conferences. It's great to be here. So today I'm going to speak about securing cloud delivery pipelines. And I would like to start from taking a look at what's going on in the industry in 2021. First of all, I want to look at the State of DevOps report. There is a yearly report looking across the industry on what practices, tooling are adopted and how they impact software delivery. And this year, we have 56% of respondents saying that they are adopting some form of public cloud. I think 21% of them, they are even adopting multi-cloud. At the same time, in the last 10, 15 plus years, we had an explosion of adoption of practices, techniques, tooling to deliver software better quality, faster. And in particular, we have the rise of continuous integration, continuous delivery kind of tooling. All the servers that go along with that, be that a Circle CI, a Travis, GitHub Actions. If you're unlucky, you get Jenkins. I'm really sorry. And so on and so forth. What happens then is that as a community, the industry really came together of looking at what are the common threats that emerge from the adoption of these tools, like configuration mistakes as we increase the complexity and the speed at which we deliver software. We really created a plethora of tools, services, commercial offerings to counter this kind of threats. There's plenty of tooling that we can use to check our cloud configuration, to detect secrets leaks, and so on and so forth. At the same time, for defending from an average hacker scenario, hackers trying to get a quick return on investment, probably any kind of offering out of the box from your cloud vendor, from your software as a service offering, will put you in a decent position to counter these kind of threats. But then, if we look at advanced motivated attackers, if the software that you're delivering contains some form of highly sensitive information, maybe trade secrets, maybe personal information of some group, some demographic that is a good target for advanced attackers, can we really use public cloud, software as a service, to protect from these kind of adversaries? In order to find this answer, earlier this year, Cabinet Office organized a Red Team, Blue Team simulation, in which I've been part of in the capacity of being the tech lead for the Blue Team. So what I'm going to cover in the next half an hour or so is some context around the simulation, how we set it up, and then I'll cover what we learn on pipelines, on architectures, practices, and processes. So first of all, again, the simulation has been set up by Cabinet Office, involving a team of builders, the Blue Team, a team of attackers, the Red Team. There is a team of penetration testers that impersonated a highly advanced threat actor. We had the luck and privilege of having some cloud SMEs from AWS, security SMEs from the National Cyber Security Center, and other HMG departments to join us in an advisory capacity. The whole project has been dubbed Team Tulip. That doesn't make any particular sense, but I'll refer to that again later, especially because that's how we named our repositories on GitHub that are available for taking a look at. I'll show the link later on. As we started, we decided that we didn't want to just build something out and purely looking at the technology, but we wanted to look at the technology through the lens of people and processes as well. So the first thing that we did, rather than starting from an architecture diagram, was to start from creating a little backstory. And we decided to scope the whole exercise in creating this fictional government agency called the Creative Licensing Agency, and trying to figure out what is their mission, what is that they have at their disposal as they start the journey on delivering service to the public. The idea is that they're building service for people to apply for creative license. They work for their personal information. We decided that this is highly sensitive. As being a very small organization just starting, we're making the assumption they have very limited budget, very limited staff. They only have a couple of very small teams. one team of infrastructure experts. They're familiar with technologies such as AWS, infrastructure as code, Terraform. And we have a small team of developers that are familiar with web technologies, Java services, React, anything like that. With this in mind, we start mapping out a possible architecture for this small organization starting. And the way we want to architect this is to try to adopt as much software as a service and cloud as possible, trying to use anything that we can have out of the box. And this is following NCSC's cloud principles, and in particular, the one that I want to call out is the idea of adopting as much out-of-the-box services as possible from cloud vendors, from SaaS. And the idea being that as a small organization starting up, any kind of security that you can have built into your tools, built into your services from your vendors can surely be better of what you can invest into at the beginning of your journey. So what we end up with is with a cloud deployment on Amazon Web Services. We start from the outset with multi-account AWS organization setup. This is following also published best practices from the vendor. AWS has the well-architected framework with well-documented best practices for how to architect all of this. And some of these, and in particular the way we set up the whole account, even get embodied into automation within the tool itself. In this case, we looked at AWS Control Tower. That is a kind of one-click solution that gives you a well-architected AWS organization out of the box with some strong opinions. And for the development and delivery tooling, we looked instead at GitHub. We created a GitHub organization, and we adopted GitHub Actions as our base continuous integration pipeline software. After creating this target architecture, we started threat modeling in an iterative fashion week by week. We created a map of what we think the main threats are, where the entry points for an attacker are in the whole architecture, how they can move laterally. And we started asking the question, this being a simulation, which of these are interesting, and where do we want to invest our time in understanding better how these attack scenarios will play out? What we came up with as an area of focus, actually, some of this is grayed out. I'm not sure you can see that graying out on the screen, but we decided to focus basically on the area in the middle, and in particular on the delivery pipelines. We tried to ask the question, well, we can assume that a motivated attacker will throw as much phishing as they can at you. Well, like 3, 6, 9 months of phishing will eventually land you an engineer's credential. What can we do once engineer in the web team is compromised, they have their credentials stolen, they have legitimate access to Git repositories, maybe limited? How far can they go in compromising the whole environment, in exfiltrating the sensitive information that we're collecting from the public in our database? I would also like to call out which areas we did not decide to go into. In particular, we didn't look at privilege access. We bootstrap the whole thing securely. This because it can pretty much be an entire research project in its own right. So we made an assumption that a small subset of the infrastructure engineers have access to some form of hardened machine from which they can perform highly sensitive operation like bootstrapping the whole AWS environment, managing AWS GitHub organization, administration credentials, and so on and so forth. Detection and threat hunting is something that, connecting them to what we discovered at the end, is something that is fundamental to a successful defense, successful security program. But we also acknowledge that at the beginning of a journey in an organization, you probably don't have the investment to really make this effective. You don't have the staff to look at the logs and try to get something out of it. So it's something that we left out of scope for the simulation. We turn off guard duty, but that's pretty much as we did. And lastly, supply chain. In recent years, there's been a lot speaking about supply chain attacks, but there's also been a lot of research on it. And we felt that there's plenty of active discourse on that. It wasn't useful for us to go through some of this once again. That said, we'd like to first speak about pipelines. If you were in track 1 earlier today, you probably already heard some of this, but I want to get back to the concept of continuous integration, continuous delivery pipelines. The core idea is that we want to have tooling that automate the way we build, deliver, test, ship, deploy software. And these tools, especially these days, are designed to greatly empower delivery teams to go on a journey of continuous improvement of their own techniques, and they can be self-managed by the teams, like with YAML files. You can commit to a repository, you can have the configuration of your pipeline in the repository, and the way you change what this automation server does is all encoded in this YAML file. That is great if you want to quickly iterate and learn how is the best possible way to build and test your software. Not so great if one of your engineers is compromised, because then you can do stuff like add very simple echo commands in the build script and exfiltrate any kind of secret that has been stored in the CI server. So with this in mind, knowing that the threat model that we're looking at is specifically looking at a compromised engineer, we asked the question, what can we do to do better than this? And the model that we came up with is what we're calling this trusted pipeline model. And the intuition is that if we go and lock down the entire pipeline and have all the build script managed by someone else, we can have trust into it and build high assurance, but we create a lot of friction for the software delivery process. But is it possible then to have a little bit of both of the best of both worlds, and having entirely self-owned, self-managed, continuous integration side of the pipeline where developers can still retain the ability of performing, of having full control over the way they build and ship the software, but move any kind of operation that requires highly privileged credentials, or any kind of operation in which we rely on some trust to be created to have validation into it in a different section of the pipeline that is not self-managed and can be locked down by administrators. The tricky part in this is really how do we make the lockdown part as minimal as possible so we can create a trust without creating friction to get into production. But still, we started with this model. What we decided to adopt for this, again, thinking from the perspective of adopting as much out-of-the-box services as possible, we use the AWS code pipeline. And it pretty much looks like this in a simplified way. We have some kind of Lambda that listens for when the GitHub action side of initial build pipeline finished. And then we pull in source code, and we essentially rebuild it. And there's kind of two models here. You can start from source code again, or you can also receive a build artifact, and then you have to kind of validate the source code and artifact match before proceeding. We made the choice of starting by simply getting in code and rebuilding it again. And then on top of this, we can layer any kind of security control, applying policy, and so on and so forth, and then performing deployment, having secret keys entirely managed within AWS itself. And this sounds alright, until we think that in reality, to build services again, to build code again, we have build scripts that are more often than not Turing complete. In the case of what we were looking at, Java services built with Gradle. Gradle as a build tool is scripted in Groovy, and you have like pretty much the full power of Groovy at your disposal to do whatever you want, really. So essentially, we're now moving the target from a malicious engineer committing changes to a YAML file that is build script in GitHub Actions to exfiltrate secrets. Now they can target a Gradle build file to call out to command and control centers from within the continuous delivery pipeline, and do stuff like exfiltrating the temporary credentials assigned to the builders, and so on and so forth, any kind of attempting takeover. With this in mind, we think, okay, coming from an engineering perspective, being the blue team, being mostly builders rather than security engineers, look, okay, what can we use? Can we throw engineering at the problem? And if the problem is that some of our inputs can be malicious, can we have some tools for started detection? Can we have customized detection rules? Can we have policy as code to detect if any of these is malicious before executing it? Well, yes, you can, but it kind of becomes a cat and mouse game. You probably start from some out-of-the-box rule sets, but then some of the tools are rough edges, and like this is an example of a very simple commit that the red team added to evade the tooling. It simply added a space and they broke the detection rules. And then as the blue team, we can look at this and say, okay, we can learn from this and like improve the detection rules. And then the red team can go, okay, fine, because I can see all the repositories, because you still want to be as transparent as possible to reduce the time to debug and troubleshoot. Then they can just look at it and create new version rules and so on and so forth. So this becomes really a cat and mouse game. So we think, okay, fine, that's our finding for this section. We'll move on and look at some alternative solutions. And we start looking instead at what we can do for boundaries and permissions, both in terms of authorization privilege and in terms of networking privilege. The interesting part of adopting some AWS native services like Code Pipeline for all of this is that we can manage authorizations at a very granular level, build step by build step, using AWS IAM. What this allows us to do is to look at the various stages in the pipeline and say, well, we can have some credentials that are available to all of these stages, or we can think that we only need these credentials when we deploy. Before the build stages before that, we don't, and we can make it so these are only available in the deployment step. That doesn't need a customized script that is an input controllable by an engineer. Vice versa, we don't need this in the build step, so we can take that away, and that's where we have potentially untrusted inputs. So we can mitigate the impact of having untrusted code running into that. Similarly, we then look at network controls and think, well, does all of this need to go out to the internet to perform builds? Well, yeah, probably yes. Building a Java service and building containers, we probably need to go and get base images for our containers, we need to get the Java dependencies, maybe Terraform modules, maybe some other bits and bobs of code from GitHub snippets. But if that's all we need, we can probably enumerate the places that we want to reach out on the internet and throw some firewall at it and say, well, at the very least, if these are the only places where we expect build scripts to reach out, we can effectively restrict to only these places. And this is great because going back to a malicious build script reaching out to a command and control center, what we can do is saying, well, you can't go there anymore. You have at the very least to trick the firewall into allowing you to go there because you're restricted to go only to an artifact repository, to GitHub, to the Terraform registry, and so on and so forth. Looking at what is the egress of the network that you need, you can filter that. Is something that can be a really useful tool to improve the security posture of a CI/CD pipeline. So that's it for pipelines. Some key takeaways that I would like to repeat in this is we have to think that some different stages, different operations in the whole software delivery cycle potentially need different properties. There is something for which you want to have fast feedback, really empower delivery teams. There's something else that needs deep trusted built into it to really work. We can try to build this differently and manage them differently instead of using a single tool to embody all of these things at one time. The ability of assigning permissions and privileges in a fine-grained manner can be a really powerful control, but of course that requires a lot more work to configure correctly. And a couple of things that I didn't really cover is then who configures these pipelines. Ideally, we want to configure all of these as infrastructure as code, but then where is the pipeline that configure all the other pipelines? Because of course that would be a source of trust. Again, like I said earlier, we didn't really look in depth at how to solve the secure introduction problem. We made the assumption that some of the engineers with the protected machines are able to set up and bootstrap all of this from a hardware endpoint, and pretty much left it at that. Lastly, going back to the issue of stealing credentials and how do we move from a self-managed environment like GitHub Actions to trigger pipelines within AWS. Looking at pull models rather than push models is a great way to avoid having credentials in less secured environments. And just a quick mention here, it's also been incredibly frustrating doing this with AWS code pipeline. Ideally, it should have the ability to trigger on git commits, but that doesn't really fit together nicely. And you can build a custom Lambda, custom thing to trigger all of this, but it's messy. So yeah, there's that. So now on for architecture, and actually, how am I with time? Excellent. So going back at the beginning, what we started from, like I was saying, is an AWS multi-account setup. The way we started all of this was to adopt AWS Control Tower. Control Tower is essentially an out-of-the-box one-click deployment of an opinionated multi-account setup. In just a few clicks, you can configure. It starts with 4 accounts. With a management account, you get AWS single sign-on to manage all of your users and access across your estate. You get an account dedicated to security monitoring and auditing. You get an account dedicated to log archiving. You get an account to start deploying your workloads. And it gives you a bunch of guardrails in the form of AWS config rules. These are rules that like run periodically and look across your accounts and tell you, oh well, there's a security group that doesn't look right. There's some stuff that is not really in line with the CIS benchmarks, and so on and so forth. And it gives you an opinionated setup for your roles across your roles and permissions across all the accounts. So you don't have to start you don't need to start thinking, all right, now that I have 5 accounts, I need to create an admin role that is valid in all of these, and provision that on SSO, and how do I design with my permission model and map that to my org. Of course, you will have to do that tailored to your org at some point, but at the very least, you start from not zero. That is great when, at the beginning of a project specifically, you have so much to do, and like spending a lot of time just to get started is not ideal. So we were very happy adopting this tool. I think that to get somewhere decent quickly is a fantastic way to get there. But the other thing for which I really appreciate all of this, I really appreciate starting from a multi-account AWS setup, is that IAM is really hard. It's incredibly powerful because it's very granular, and you can do like very complicated, very advanced stuff with it. But there's just so much of it, and it's like, you know, like the time spent to create a very nice lockdown, precise policy and test it and make sure that there's no possibility of escalation is a lot. And what happens more often than not is that then you would rather start with an AWS managed role, and these are often overly permissive. So with all said, what can we do to reduce the impact of takeover by permission? And separating workloads, separating databases, separating any kind of thing you do across multiple accounts kind of provides a natural boundary there, because then to share resources across accounts, you really need to be explicit about giving permissions, sometimes even on both sides, if you think about how do you do across account assume role. So that's fantastic, because essentially it's saying it makes it really hard to do the wrong thing. So starting with multi-account is something that I will always recommend for how simple the thing that you're going to do with this account will be. think about adopting more than one account from the start. And if not, a control tower, because that enables config and that costs money. At the very least, starting with SSO, that is for free, is a good start. So that's it for account boundaries. And then on a different kind of boundary, I want to think about security groups. So I'm going to move towards the application side. And what we built as part of this is a very vanilla two-tier kind of application. We have a Java web server, show some pages, receive some forum posts, connects to a database, fronted by a load balancer. Nothing special, nothing fancy. But the interesting thing with all of this is that we start with a fairly classic divisioning in subnets and security groups, and pretty much by default, we tend to start with a way of enabling egress to the network from all the stages. But then we looked at the web service, and then we looked at what the red team could do to us, and some of the things that they did try and did succeed into was to commit some malicious code within the web application that once deployed will reach out to command and control centers. We looked at this and thought, well, actually, do we need to allow the application to go out to the internet? Well, situational. For us, the answer was, well, actually, no. It's just a thing that, like, receives a request on the internet, displays a web page in return. Some time ago, like, if we deployed this on an EC2 machine and managed the server, then we definitely needed to go out on the internet because we'll need to patch the server, we'll need to run apt update or any kind of other thing. But if we think of building all of this with techniques such as immutable infrastructure and continuously rebuilding the base image and destroying that and rebuilding that rather than continuously patching that live, or using containers for this that can achieve the same results, then we don't really need to reach out to the internet. And we can remove egress entirely and cut off the ability of for the red team to reach out to command and control centers. So this was a quite interesting win. We deployed all of this on Docker containers on the University Container Service, so it was trivial for us to achieve. Of course, depending on what your web services are doing, you might need to reach out to the internet. An example, if what you're implementing depends on some third-party API. But that doesn't mean that you can't look at your architecture and thinking, well, actually, maybe in reality I'm moving towards microservices and I can break down this one service in a part that just displays website and interacts with users, and some like back processing part that is deployed separately and has access to the internet. And you can potentially obtain some better segregation out of this. And then we can take these ideas a bit to an extreme and say, well, actually, we're managing all of our users, all of our AWS users with AWS SSO rather than being AWS IAM users. And if we're doing this, we can adopt a service control policy and say across all organization is not allowed to create IAM users in the first place. And as a consequence, we can't have AWS access keys and we can't have AWS console passwords that can be leaked and stolen and get a foothold inside the organization. And now I'm being a bit extreme because of course you definitely have some cases in which you kind of need to create an AWS IAM user to integrate some tool or something else. But you see where I'm going with this. Like, if you put some effort into it, you can look for opportunities to take away pieces of your architecture or shift that so that you can reduce your attack surface. So once again, learnings out of this: don't allow what you don't need, and do think twice about what you really need for your application to run successfully, for your SDLC to complete successfully. Consider adopting immutable infrastructure if you're not already. That can give very nice security properties that we can leverage for all of this. And last but possibly the most important out of this, account boundaries are a fantastic bulkhead. I would definitely recommend adopting this. Last one up, practices and processes. So we touched a little bit about policy as code earlier and configurable detection rules. We looked how that can become a cat and mouse game, but we also discussed that as something that we put in a pipeline to try to prevent execution of malicious code before a pipeline will execute that. But it's still running within a pipeline. The thing that really surprised us is that the very first attack that we suffered from the red team was not an attempt to take over our pipelines, take over our environment, it was an attempt to take over our engineers. The very first thing they tried was to add some malicious snippets inside the gradle build files, meaning for some other engineers to run their build locally and recover their credentials and take over their accounts. So they tried to pop a calc on Windows. Lucky thing for me is that I actually run Ubuntu desktop. We don't have a calc. You have to write it and compile it yourself, so I'm safe. But that said, all this policies code kind of tooling doesn't really save you from this. And similarly, there's other attacks that the red team managed to slip through. Once we cut away the ability of reaching out to command and control center from malicious code in the web services, they thought, oh well, if we can't reach out to the internet proactively, we just can create a backlog for ourselves. They essentially added a web shell. So this bit of code is, in the context of Java Spring Service, is just one more endpoint with some obfuscated names that an attacker will know, and it just passes any kind of HTTP request straight into our OS shell and sends the result back. So being this response and not a request, then they can avoid the barrier of egress filtering entirely. By the way, as a parenthesis, we tried to throw AWS Web Application Firewall at this, and it did absolutely nothing, especially when the commands that we receive are something simple like ID, who am I, and stuff like that. It was just like, yep, that's fine for me, even with base 64. But the reason I'm raising this again in the context of people and process is that as we started adding better rule sets for detection into this, that detected simple stuff like, oh, you're using an exec in your Java code, this is a bit uncommon and very, very dangerous, maybe you shouldn't. Then the way they avoided that was to introduce metaprogramming in Java that's reflection. So instead of saying, well, java.exec, I can say, hey, Java, give me the method name exec and execute that for me, please. It's more convoluted way to execute stuff, more obfuscated way of executing stuff. But as they start adding obfuscation in the code base, this starts looking weirder and weirder. And for a machine, for a rule set written down, this allows evasion. But what if we have a person looking at this? Suddenly, all of this is starting to really pop out to a human eye. And this leads us to speak about code review. Getting into the simulation, especially from the perspective of a builder that is a proponent of trunk-based development, of trying to deliver software faster and avoiding big lead times, we came in trying to avoid doing code reviews and thinking, can we do better detection engineering so that we can push later down the line any kind of stage of manual approval and just like use good delivery techniques, good coding techniques ahead, and not have this, oh, I have to submit a pull request, I have to wait some days, a week for someone else to review it. And that was yours done. But what we learned out of this is that if we are trying to defend from attackers that have access to the code base, some of the attacks, the only way you have to find them is to really have another human to look at that. But the other thing that we thought is, well, how does that work in the context then of using agile methodologies such as pairing? By default, we usually work with a pair of people working on the same code at the same time. Can we really use this as a code review? More often than not, in my experience at least, what happens is that you have two people pairing on the same machine, they work together on something, and then they just commit and push straight to master, straight to main trunk, however you call it, on the same machine. And that kind of counts as a review. And that really doesn't necessarily protect from these kind of cases. You still have a single identity, a single credential being allowed to push code, possibly all the way into production. But if we take this and add a technical control on top of this, that is something like a branch protection, and enforce as even a small-lived pull request, and combine the two things, then we can have some guarantees that are fairly strong in this. We need, because of the branch protection, at least two people to approve code to be merged into mainline before getting there. And this is compatible with the same two people looking at the same screen and working on the thing together. But then one of the two will have to jump on their own machine to run the approval. But this doesn't have to happen in a day, in 2 days, in a week. It doesn't have to slow down the process. They have all the context of what they just seen working with a colleague, and they can just quickly go through it, have a fairly quick review, just checking that whatever they see on their screen, on their machine, matches the expectations of what they just worked on the machine of a colleague that might or might not have been compromised. They can have this out-of-bound kind of approval, but still in the flow of the delivery process. So in conclusion, we feel that in reality being able to have an effective way of doing code reviews is one of the most powerful controls that you can have and you should have in the way you deliver software. And it's not just about having two people looking at the code at the same time. You need some form of technical control, but this doesn't have to be introduced in longer lead times. So once again, in summary, detection evasion is a bit of cat and mouse games. But the good news is that the better detection rules you have, the easier it will be for a human to catch stuff that becomes weirder and weirder. Similarly, what we also observed as we went through this is that good engineering practices also positively contribute to this. Things like having code that is self-descriptive, having smaller classes, smaller methods, smaller pieces of code that are less complicated, having more simplicity in your architecture, having stuff that is well tested. All of these make for easier detection of weird implants in your code base. Cool, that's the end of it. So, in conclusion, getting out of this whole exercise, our feeling is that the security bar that is achievable in the public cloud and adopting software as a service is possibly higher than many believe, but it does need attention to design. In particular, our overall system is definitely less secure than the sum of its parts, and the devil is not only in the details, but in the details of how different pieces of software, different services connect together. When we have these boundaries between, say, GitHub Actions and AWS, that's really when you want to put your effort on checking how you're piecing together the whole solution. Architectural controls can be really powerful. Do think about what you can take away from your architecture, how you can shift it to improve your security posture. And good engineering practices do impact positively security, can help having a better view across your software estate with automated tools, and can help humans to have better, more efficient code review. And lastly, once again, true set of eyes does not necessarily imply longer lead times and friction for a delivery process, but in order to have that effectively for security, you also want to have a technical control added to that, and not simply the act of having two people in front of a single screen at the same time. That is, and lastly, check out the repositories. All of the stuff that we wrote is public on github.com/teamtulip. So there's a repository that is called Tulip, where there's all the documentation, all the ideation, weekly threat modeling sessions, and so on and so forth. Everything else is a mix of the example service that we built and some infrastructure as code of the whole estate. So take a look, have fun, hope that it's useful. And that's it for me. I think I have a few minutes for questions. Excellent.